In this item we've got a tube A frame, but the stories are not the same height. We also notice that the beams are not at the same length, although they are the same EI, and the columns, of course, are of varying lengths. It turns out that the right half is about half of the left half panel here. We get a lateral load of 20 kips, right? We have a moment resisting frame system, so all connections are rigid, and we do have fixed supports. We're asked to provide a guess as to the deflected shape and the related moment diagram, provide brief explanations to support our guess. So let's handle that first off, and I'd say I'm going to start with the notion that, okay, as I push this frame to the right, the whole thing is going to want to sway to the right. That only makes sense. We're not going to let the elongation of AB be anything other than 0. But when we look at this column BC, that CD part's going to want to go to the right too. And so I don't know how much that's going to go to the right, but it's going to want to move over to the right. And we're very used to that in this kind of response we're going to get reverse curvature to pretty much everything, so that shouldn't change any. Note that we've got, let's start with the beams here, and let's not make the rotations at the top of the beams too big. Flexion point will probably be roughly in the middle, and again, let's not make the beams go too much, but we get a little bit of an S shape there. We're going to get S shapes in the columns too, so right angles remain right angles, so we're going to get an S shape in that big tall column, something like that. Looks like I might have rotated joint A just a little bit too much, and same thing at B, it probably rotated it just a little too much. It's going to be hard to really get that S shape in there. Well, we get two S shapes, one for the top and the bottom half for that middle column. And so that goes along with the resisting moments at the base, and then the reverse curvature that we have to have up at the top that goes along with then the moment diagram, which I don't know if this will be convenient or not, but I'm going to superpose it right on top. We're going to get, if the top and bottom of the column AE had the same moment diagram, then same moments, the same end moments it is, I'd get a moment diagram that looked like that, inflection point about in the middle. Same thing in the beam. Excuse me. And then we get a microcosm of that for that little top half of column in the middle, that BC portion. CF will be something like this, and likewise then for the far right column, and then this middle will be a moment diagram that looks something like so, right? And all those are consistent with each other, right? So that's going to be the key thing. I would use then my knowledge of moment diagrams and the point loads and the variations that have to be happening at the far ends to explain why the moment diagram has to have the shape that it does, as well as look at the equilibrium of the various joints to indicate that I have to have either moments that are equal opposite to each other, or in the case of this T-junction, I have to have two of them going in one direction and one going in the other in order for that to be in equilibrium, to help explain that. And then you could use that moment diagram to explain the deflected shape, or you could use the deflected shape in your anticipation of it to reflect what you think the moment diagram is. That's how I sort of presented this, plus your knowledge of what has to happen with the point loads being where they are at the joint, yet we're having bending, so that's going to create the situation with sway that we've got for the moment diagrams. All that is consistent, and I'd feel a lot better if we finished off some of our reactions here. The shears are going to be going in obvious directions, and then you've got the overturning from the axial forces, and maybe that middle one is about 0. Not quite sure what happens with it, but it will be about 0 because it's sort of like at a neutral axis. Right? And then we were asked to, for part B, for the slope deflection model, identify the kinematic degrees of freedom, the number of equations needed, the unknowns in these equations, and write the equilibrium equation. Set up, do not solve for the unknowns, and don't write the slope deflection equation itself unless you really need it to figure out what's going on. So for instance, we know that we'll have theta A not equal to 0, theta B not equal to 0, theta C not equal to 0, and theta D not equal to 0. So E, F, and G will be 0. So we have 4 kinematic degrees of freedom just from member end rotations. Then we've got sway. So delta A will be one of those, but that will be the same sway that happens at B. So that's just 1. Let's call that delta 1. And likewise, however much C moves over, we can call that delta 2. That's the same amount as what D moves over, so that's delta 2. And if we know those two, then we know what happened. Oh, we know everything. So we've got here then 6 kinematic degrees of freedom. We've got theta A, theta B, theta C, and theta D, and then all the chord rotation terms can be determined through this delta 1 and delta 2 as our displacement degrees of freedom. Alright, and so note here, for instance, it's easy to think about psi AE being associated with delta 1 over this 24 feet. Right, so that would be one example. And that would be related to, well, not related, but we've got also, say for instance, delta or psi CF, that's going to be equal to delta 2 over 12 feet. That is the same as psi DG, but I've not included the psi for then BC yet, and that's because we'll have to look at delta 1 minus delta 2 over that 12 feet in order to get to that one. So that's a little bit more complicated. That just emphasizes it's the drift, story drift, the interstory drift that matters for that column, not necessarily the raw displacement itself. Right? So that's a little bit more complicated, but that's how those would be set up and why we end up with only 6 kinematic degrees of freedom here. Right? Now the equations that we need are going to be one for each, and they're equilibrium equations. What's going to happen is we'll go to each of the associated joints. I'm going to go to another sheet of paper here to begin to write this out, and I'm going to keep that portion available, the drawing available to us. So we would go to the first kinematic degree of freedom, theta A, and we have then just those two members that frame in, and so that would be then our MAE, and our MAB, and our equation would just be MAB plus MAE equals 0. Then we go to joint B, have a similar setup there for all the members framing into that joint. And of course the equation would be MBA plus MBC equal to 0. We get 2 more rotational degrees of freedom to work with, theta C and then theta D. Just go ahead and begin to get that written out. There's the stems of those. I'm going to do the simplest one last. There's your MDC and your MDG. Simpler because it only has 2 terms in it. But now let's go to this middle one. We've got MCB, we've got MCF, and then MCD. Note, remember, we're doing this in terms of the positive sign convention that we've established. So there's our 4 equations of equilibrium. Those are all associated with just the joint rotations, those kinematic degrees of freedom that are the joint rotations. But now we've got to go get the equilibrium equations associated with sway. This is a lot trickier, right? Probably going to take us maybe a lot more to deal with this. One thing I might think about is I want it in terms of member end moments. So if I knew something going on here, here, and here, those member end moments, that might be kind of helpful. We've got those shears involved. So one thing I might do is I might start with just looking at the various columns that we've got going on here. There's that's A at the top, E at the bottom. We've got clockwise positive on the member end. So there's your MEA and MAE. And there's the shears that will go along with this. And so from that I know that VEA times 24 feet is equal to MAE plus MAEA. So that's part of it. Only part of it though. We go over and we get the short column CF, and again clockwise on the member end. And so VCF, VFC, so that makes 12 times VFC equal to MCF plus MFC. Alright, and then there's one more of these. Alright, there's the far right column. Well, we think we're just playing with this. We have to see how this is all going to work out. This would be DG and MGD. Again, plop those in there. FGD, FDG, and FVGD is going to be 12 VGD is equal to the sum of that MDG plus MGD. Why the heck do I care about that? Well, from the global, I'm going to get then that the way I've got this set up, all these shears are going to the right, so 20 kips is going to be equal to the opposite of each of these, VEA plus VFC plus VGD, of which then I've got then all these little pieces that will feed into that. Alright, well that's I guess okay, because I got one equation now in terms of all of those, but I need one more in here because I got delta 1 and delta 2 involved. So I got to do one more thing in here to somehow get that other sway involved. I've used that column, I've used that one and that one, but I've not done anything with this one right here. So that's kind of interesting. So now let's go look at that column, and there we're going to get M. Let's see, this is BC, so that's MBC. No, it's not either. That's MCB at the bottom. At the top, we have MBC. And now there's our shears, VBC and VCB. Now, how the heck is that going to be helpful? Well, one thing I can figure out is VBC is equal, 12 VBC is equal to MBC plus MCB. And if I go back here, and maybe if I just do that portion of the free body, I'm just kind of making this up here, trying to figure out something that might turn out to be useful, playing around with various ideas. And we've got there for that one, there's your 20 that we applied. We've got then this is EA. Of course, we have an axial force in the bending moment there. And over here, we've got a shear that, let's see here, that's got to be going in the, VEA was shown going that way, and so VBC also, by the time we flip it around from here over to this side, is going to look like that. Of course, again, a moment and another value there, but notice again, now we get 20 minus, or equal, sorry, a minus VBC plus VEA. That's a different equation than we had before, and because we have VBC now in terms of member and moments and VEA in terms of member and moments, we've got an independent equation, and so that's where we'll get our equation 5 and our equation 6 from. That will help us to do what we want for the slope deflection method. So let's make sure here that we've gotten everything that's been requested. We provided a guess, we provided an explanation, slope deflection method, identify the kinematic degrees of freedom over here. The number of equations needed, we need 6. The unknowns in these equations are these right here. So they're equilibrium equations in the unknowns, which are the member end displacements and the general sway terms. Set up, do not solve for the unknowns, which is what we've done with those equilibrium equations. We've written those. We can generally write that ultimately as these will be, what would they be? They would be the equivalent fixed end forces and moments are going to be equal to some stiffness matrix times this vector of all of these right here. These stiffness coefficients, these KIJs, are going to come from looking at accumulating all that slope deflection mess. Alright, so we have MNF is equal to 4EK theta n plus 2EK theta far minus the 6EK psi terms plus the fixed end moment terms. And so a lot of these here, those fixed end moment terms are going to accumulate and go into here, but we have coming from these sway equations, we're going to get some other effects in here. So that's why I generally call this the fixed end forces terms, and then all get substituted in, and away we go. We'll solve for those unknown member end displacements. Equilibrium equations in the unknown member end displacements.